Hi there. Um, in this session, that's session 5 of programming from the very basics using Python, we will continue where we left off in session 4. That's ingredients of a Python program. There's a part 3 of the series. What I'll plan to cover in this video would be mostly to do with statements and expressions. Continuing from there, I'll talk more about expressions in this session, where I'll talk about literal value representations of numbers and how do you formulate arithmetic expressions, and also about comparisons. How do you compare values? What are the different syntax grammar supported by Python in terms of the operators and also the Boolean logic available on it? And we'll also look into conditional expressions. When it comes to expressions per se in Python, there are way too many ways you can represent expressions. When you talk about literal value representations and identifiers, function calls, arithmetic expressions, binary bitwise operations, value comparisons, Boolean logic comparisons, conditional expressions, subscripting and slicing expressions, comprehensions, and the yield and await expressions. Well, there's a whole lot, right? I will not be covering all of it in one single session. Obviously, this might be a little too overwhelming. So the best way to cover it is take one at a time, go a little detail into it, and then we will connect them all together. And that's where we'll see things functioning together, right? And if you look at even statements in Python, there are way too many statements. We have simple statements where you can actually treat an expression as a statement where it makes sense. Like a function call, for example, functions that don't return a value can be generally treated like a statement. And assignments are another part of simple statements, and there are different kinds of assignments supported in the Python syntax grammar. We will be covering assignments separately in a session, right? In the future sessions, I'll talk specifically on assignment, where I'll talk about different ways you can use assignment and what happens under the hood and in Python, and also what are the things you should know about when you're dealing with Python code when delving with assignments. There are also related assignments. We have deleting references using the del statement, and there's also about modules in Python. So we can load a module in Python. So what are modules? For now, I can tell you that modules are a means of reusability in Python. So it's some kind of code that you would have written. You want to use that code elsewhere in another Python program. You can represent that piece of code, right, as a program which you've written as a module. And you can use those modules in other programs. And this way you can emphasize reusability. In fact, modules are the core of Python design, I would say, because if you're dealing with any sizable Python project, it's very likely that you'll be using some module written by somebody and using them for your own use case, right? And this saves a lot of time because you will not have to write everything from scratch. There are a lot of modules available within Python when you install Python, runtime on your own. These are part of the Python standard library, you can call them. So we can call them libraries, right? What you call as libraries in other languages, they're emphasized as modules in Python. So they are means of modularity and reusability, which are two important aspects of program design, right? We'll go deep into it in a separate session again. There are also ways you can raise your own runtime errors and exceptions, which is useful when you're trying to build some reusable code. So when you encounter an unlikely scenario in your code in runtime, you want to just flag off an error and say your program cannot continue any further. You could do that by using raise statement. There are ways to even handle these kind of exceptions, which is there in a compound statement, which is there below, which I will show you. There are also assertions that can be done in Python. Basically, if you're writing code which uses a test-driven development approach, where you want to test your code and make sure the code works as per specifications, right? This is basically called test-driven development. In order to aid test-driven development, we use assertions. And in order to apply assertions, a statement is used. Mostly it is used in unit testing frameworks if you're going to be using them in Python. There are frameworks like unit test, and which is built into Python standard library, by the way. And there are more reliable third-party frameworks like PyTest, which people use for unit testing. Test driven development is a means of developing code that you know that it works for a given specification. So how do you know that your code is going to work exactly as per specifications, as per requirements? You formulate test cases based on the requirement, right? For example, if I'm going to say that I want to write a program to find an area of a circle, you want to know that this code works as intended. So you formulate test cases where you put in some known values for the radius, let's say, and and you know the value, what is the area for that. You verify that. You verify for some known values, and then you can formulate a test case around it and say, yeah, this works. And you can also formulate test cases where it breaks, right? For example, if you pass a non-numerical value for a radius, it should obviously break in a more graceful manner. So those aspects are formulated in testing. So we'll talk about that in a separate session again. So each of these bulleted points which you see here are topics for separate sessions. Each session, right? We will be delving into it in depth. And there are also other things which are like loop controls, which is done using break and continue, which is part of the compound statement. Again, on its own, it's not very useful. But if you're building looping constructs, which you'll see in the compound statements listed below, there use break and continue for loop control. And if you're defining your own functions, you can return from a function a value that's done by return statement. You can use yield semantics, which is a Python specific feature. Yeah, it's there in many other languages too right now, but it is popular in Python, where you can transform a function into a generator by using yield statements. And there's also global and non-local declarations. I told you that in Python there are no declarations, but there are some caveats. So we'll talk about that when I talk about these features in the further sessions. We'll also look at type statement, which is recently introduced in Python 3.12. I am not a fan of these features, but these are some new things that's getting into Python, trying to make Python more type safe, sort of type safe, like other languages which are compiled, right? So it's a new feature that's going on to Python anyways. So we also have compound statements, which are the core of most sizable programs. So when you're writing a program, your program will require to take some input, and you want to compare the input with some value. And if that condition is met, you want to perform something, right? We have conditional statements to handle that. The if condition has been there in Python for a very long time, but recently in Python 3.10, they introduced another condition called match case condition, which is similar to the switch case conditions that you'll find in languages like C, C++, or Java. There are loop control statements, or looping statements rather, which is while loop and for loop. They're just two kinds of loops in Python. And we'll discuss more about that in a dedicated session again. And we have ways to handle exceptions, runtime errors. That's by using try except block. We can also use context management. If you ask me what is context management, there are certain resources which we can access in your program. What are resources? Things that we are not managing within our code, or rather not fully in control in our code. For example, I want to open a file and read contents of a file from within a program. But then to open a file, I can't do it on my own. I need to take the help of the underlying operating system. The job of an operating system is to manage resources, right? So if you have a computer, when you boot your computer, you boot it through Windows, or you might be booting through Linux or macOS. What are these? These we call them as an operating system. The job of an operating system is primarily, in a very simplest of terms, resource management. They manage all the resources. What are resources? The resources could mean all the parts of your computer, your CPU, the memory, your storage, that's your disks, right? Your hard drives or your SSDs and pen drives, all your storage media, where you store data as files and folders, and network, your graphics, your IO devices like your keyboard, mouse, your display, your webcam. So all of this stuff, these are resources which are fully managed by one single big piece of software, which is the operating system. The job of the operating system is to manage resources on behalf of applications running on top of them. So when you're writing a program here, the programs do not directly communicate to hardware. Rarely they do communicate to hardware. Most programs take the services of an operating system in order to talk to hardware. Think of the operating system as a broker, as the person in the middle who is going to abstract out the intricacies of the hardware and provides a simple interface for it to communicate to it. It's like you want to manage a very complex equipment. You don't really do it on your own. You hire somebody who's a specialized technician to manage the equipment. And you just tell that person, do this, do that, and he's going to follow your instructions, very high level instructions, and know how to maneuver the hardware. So we have this kind of specialization, right? For example, if you want to travel by flight, you should, I didn't know how to fly an aeroplane. Not many of us do that, right? But we have specialized people who know how to manage the aircraft, the airline staff. They are the people who manage the aircraft, the pilot, the stewards, and all of people who are there, right? And we just go, sit, relax. We say we want to travel to this point, and they take us there. The point is the intricacies of managing all those internal processes are hidden away from us. That's how, when you're writing applications in all the modern computers, sophisticated computers, we need an abstract layer to build on. For example, how to display something on the screen. I don't have to worry about all the intricate details about what kind of graphics processor I'm using, what kind of GPU I'm using, or what kind of display I'm using, and all that. The operating system manages them with some kind of device drivers. And we just are given a very simple interface where the operating system says, if you want to display something on the screen, just call this function that I have, and you just have to invoke that function. These are called as system calls, right? So when you look at files, are merely an abstraction of data stored on disk normally. You can tell an operating system, please open a file for me. The OS is going to open a file. Now, when an operating system is opening a file, it has to maintain a context for the file. Because the file is open, it must be closed. When you say I'm done with the file, the operating system will release the resources, which is managing for that file. So this resource management can be done in a more cleaner or a more tidier manner using context management clauses like with block. You manage files, locks. We have these locking mechanisms, which you'll learn when I talk about concurrency in the future advanced training sessions. So where I'll talk about how do you write two threads of execution, and if they want to share resource, how do you manage them with locks, right? So lock management is all done with context management blocks like with block. If you want to use a mutex, even network sockets, if you want to communicate over the network, you use something called as the socket API at the low level, and they can be managed with block. Database connections, connecting to a remote database to send and retrieve data, or store and retrieve data, let's say, can be also done with context management. So all these are resources not fully in the program's control, but mostly managed by operating systems or other services on top of operating systems, are best managed with resource management support. We call them as context management in Python. Detour a bit. I'll go a little detailed into context management with examples when I talk about file IO in the further sessions. We also have component definitions for defining function, defining classes, or defining something called as coroutines, which is done with the async def keyword introduced from Python 3.6. Coroutines did exist much earlier, but the syntax were having some weirdness into them. I think in Python 3.6, they introduced a new keyword called async, an await keyword they use for building coroutines. So we'll discuss that in the further session. So we can see all of these are different kinds of statements and expressions that are supported in the Python language. I mean, if you know these aspects, you can say that, oh yeah, you mastered Python. Most of the syntax grammar is only this much. When I say only this much, each of them have some depth to them, which I will cover in each of the future sessions. But for now, in this session, what I'll talk about is, first, let's talk about the expressions here. Now let's go back to expressions. If you're continuing from the previous classes, that is, let me create a new block below. Yeah. new cell. Now, I told you that an expression can merely be a literal number like this. This is a valid expression. Okay, I have to select Python runtime. Keep forgetting that. Ignore this error. Run this one more time. This is a literal notation of a number. I think I talked about that in the last class, last session. So this is also an expression. It's a valid expression because when you put this in your REPL, you can see it returns a result. And more often, you can actually assign this to a variable. You can actually use something like v is equal to 56. And when you actually say v is equal to 56, and you can just print v, you can see that it shows up 56 in here. Now we can actually look at this. This is an assignment statement. An assignment statement has an expression on the right hand side and an identifier in the left hand side, right? We have an expression in the right hand side, an identifier in the left hand side. This identifier, I told you, are like labels. I keep repeating that again. And these identifiers are called variables. You can also call them names. That's the Python term used. So let's look at this. One interesting thing I should tell you. If I go to the next cell and just put v here, now I'm using an identifier as is. An identifier can also be used as an expression once it is defined. You can see that. The value of v is 56. V is representing the value 56. What if I look up another identifier which I have not defined? For example, what if I try to print a value x? X, I just press Control Enter here. It throws an error. If you see an error that shows up like this in runtime, name error, name x is not defined, or name, whatever name is not defined. What this essentially means is that you have tried to access an identifier which is not yet being defined. What it means is that you're using a label that is not assigned to anything. You can't have a label hanging in the air. For example, you just can't have an identifier which is not assigned to anything in Python. Let me give you a more real world funny example. Maybe if you go to a supermarket or a grocery store, a bigger grocery store, and where you can pick up stuff, right? If you go to all these malls and you can pick up stuff on a basket, and you can go and get it billed at the billing counter or the cash counter. It's a very common thing in the cities, right? If I go to all these big groceries or big stores and pick up a lot of stuff, I could pick some grocery, I pick some snacks, I'll pick up some stationery, I could pick up some household needs, maybe some cleaning stuff. I put them all on that tray, on the basket, and when I go to the billing counter, at the billing, they don't really care about what you really picked up. They care about the tag that's on it. Mostly you have a barcode tag on it, which they sort of scan. That's what the norm is these days, right? They scan the barcode, and automatically in the billing system, you have that information about it is shown up. That barcode scan that is there, the barcode tag that is there, or the sticker that is there on that product which you bought, that is the identifier for the cash counter, right? The people at the cash counter, at the billing counter, they don't really care about what product it is. They only care about the tag on it. Now, every product that you get from this grocery or the supermarket will have that tag. But what if I do this? I walk into a go to a shopping mart, and I see one product, maybe a bag of chips or wafers, whatever you call it. I don't pick up the wafer. I see that barcode on top of it. I peel that off. Maybe it's a sticker. I peel it off. I go to the billing counter and say, I just want to buy the sticker. I don't want that wafer. That is not generally allowed, right? I mean, nobody will sell a sticker. The sticker has no value on its own. The sticker that's on that particular bag of chips, it makes sense only if it is on the bag of chips. When it's taken off from there, it has no value. It has No, it doesn't make sense to even use it in any case, right? In the same way in Python, if you're dealing with all kinds of data, you first create the data and you identify it with an identifier. That is a label, that is a variable, which means you can't have a variable that is not assigned to anything in Python. You can't have an undefined variable. You can't just say, I want to have a variable called X, but it's not defined to anything. That is not supported. So some people would say, oh, okay, I want to just initialize X with a magic value called none. Some of you might ask, what is that none? None is representation of nothingness. Oh, you can do this. And now when I actually try to put X here, it's going to print nothing. It shows nothing. As an expression, it's nothing. If you try to explicitly use a print function to print it, print of X, it prints X is nothing. So none is a special literal, I would say. It's not a literal, it's a keyword. Technically, it's a keyword that represents nothing, that can be used in an expression. But you know what? You should avoid statements like these in Python. This comes from Java programmers. People who come from statically typed world, mostly like Java, they will declare variables and pre-initialize them to null in those languages. And they follow the same norm in Python. I've seen a lot of Python code where they have a line, they have the first few lines like, name is equal to none, role is equal to none, or against a connection is equal to none. And I asked the developers, why did you do that? Oh, we are going to use those variables later on, so we're just initializing them to none. It doesn't make sense. If you're working on Python, which is a dynamic language, when you define a variable, you define with something useful. You don't define and say, I will use it later, so I'll initialize to none or initialize to none. This might sound okay in the statically typed world because storage for variables are pre-decided during compile time. When the code is getting compiled, I think I talked about this, the compiler has to know about these variables, what are their storage, how much space they need, and what types they represent and all that. We typify variables, so it might make sense. But in a world where things are dynamic in runtime, there's absolutely no need for you to define a variable, predefine a variable to nuns and then reassign it to something else later. There are some logical use cases where you might want to legitimately pre-assign a variable to none and do certain things. Unless there's a logical requirement, it is best avoided to pre-initialize variables to none. That's one important thing to keep in mind. If you want to make your code look Pythonic, I'm using the word Pythonic. We'll talk about that. So when you're writing Python code, in the Python world, they say, oh, how do you make your code look more appealing, more Pythonic, they say. Like there's something called Pythonisms in Python world, right? There's a lot of wit and humor around it. So here, this is not Pythonic, I would say. This code does not look like Python, doesn't resemble the Python way. So avoid this. I would say avoid statements like this. There are a lot of other legitimate use case of the none keyword, which I will discuss mostly when it comes to function prototypes and all, right? That's where it's used, but statement like this is best avoided. All right. I told you that V is an identifier, which is defined with a value here, 56. Now I can assign one identifier to another. I can just say maybe X is equal to V. This is perfectly fine. Now you print both X and you try to print comma V, both will show up the same value. Which means that an expression could be an identifier itself. An expression could be an identifier that is defined to something. So when I put an identifier there, like a variable, in this case, I put a variable V here, what V represents, X will represent the same data. You can see that I'm wording it carefully. V is representing 56. So X will also represent 56. That's what I mean. When I go one layer deep, specifically on assignments, you'll understand about this concept of reference copying, right? Copy by reference, we say. So we'll talk about that in the further session. But just note that your expression can be either an identifier, it can be a literal value like you see here, literal notation of a value, or it can be some expressions like arithmetic expressions, bitwise expressions, and so on, like this entire list of things which I showed you, list of things that I showed you in here. All of these lists can be any of these things, right? Now let's talk about the literal representation of numbers. If at all I want to represent a number in Python, you can just say, I can just say maybe a is equal to 1, 2, 3, 4, 5. And I can say print a. Yeah, it's a number. It's a no-brainer. It's a number. And I also told you that the moment you enclose this in quotes, it is no longer a number. It is now a string. So this, based on this literal notation that I had it here, Python creates a string object for this syntax when you have data that's within quotes. And as I told you, it can be double quotes, triple quotes, single quotes. There are different kinds of quoting. But for now, I'm just using double quotes. When I talk specifically on strings, I'll tell you different ways you can represent them. Now, how do I know what is the type of an object? In order to identify the type of an object, there is a built-in construct in Python, which is called type construct. I can say type of A. You should be very careful. You should watch my words very carefully here. I did not say type function. Type looks like a function, right? What do you do here? I said type. I said type of A like this. Looks like a function call. You're calling a function. I told you a word, open close parenthesis. It's a function call, right? Print, open close parenthesis, calls print function. Type, open close parenthesis, should call a type function. Is type really a function? Not really. A type is a type. There's a identifier called type that represents an object of type. I know it's confusing. There's something called type in Python. There's an object called type in Python. And this object can be called like a function. Right? This type, right, can be called like a function. When you call it like a function, when you pass one argument to it, it has different syntaxes. You pass one argument, it'll return what type that object is. So as a type of A, it shows this A is referring to this particular string. So it identifies, this particular data, whatever. I don't know it's a string, it's some data. So when you pass this as an argument to type will identify what is the type of this object and then print it in this kind of a notation. You also note that in a REPL, when you try to invoke certain expressions like type, for example, in this REPL, it only shows str. But instead of using simply type of A, if I say print type of A, using the print function as a print type of A, it more explicitly says it's a class called string. What it means to say is that this particular data is an object that belongs to a class called string. Now we have class and objects. Class and types mean the same thing in Python. I should be more specifically from Python 3.0 onwards. Before Python 3.0, the story was a little different. Okay, so we have new style classes. So in Python 3 onwards, that is since 2008. If you've been using Python since 2008, that's Python 3.0 onwards. When I use the word type or when I use the word class, they essentially mean the same thing. What are classes? We say objects. For example, if you remember yesterday, the last session, I showed you this is an object. What is the object? It's an object of class mouse. It's an object of type mouse. The same thing. Whether I can use the word type or class. This object belongs to a class called mouse. So what exactly is a class? A class is merely a specification of a certain category of objects. It's a specification for an object. So when I say mouse, like the computer mouse, you know that a mouse is a pointing device which is used to point things on the screen. It has buttons on them. the different mouses have different kinds of buttons. I still know the Apple mouse had one button, right? But all our PC mouses have two buttons. And these days we have a scroll wheel. And some of the mouses, like some exotic ones, might have extra buttons. Like I have one of them, which is there here. It's got some extra buttons on the side. It varies. But still, it belongs to a class called mouse because it's a pointing device. The classes mainly represent the behavioral trait of an object. The behavior of an object is mainly represented by its class. That's what a class should represent. I say a class called pencil. I say pencil. Your mind just thinks this. This is a pencil, right? So when I say a pencil, it's obvious that it might have some kind of a graphite lid, which you can write, and you can sharpen them. This wood can be sharpened. That's a typical trait of a pencil. So this is a class, the class called pencil. This is an object. This is an instance of pencil. I could have many pencils. I have any more here. Hang on. Yes. So these are two different instances of a pencil. You can see how I'm using the words. I'm using the terms, right? See, when you're learning programming, any language, you should be very careful about the terms you use. That shows how good you know about the language, right? The right terms. So I say, this is an instance of type pencil or class pencil. So is this. Both are instances. Each instance will have some changes. For example, there's a change in this pencil. For example, this is yellow and this is a little stripe with grays and blacks on it. And this pencil has a eraser on top and this does not have. So there are some instance specific properties which are different from each instance. Oh, this pencil is short, this pencil is slightly longer because I think I use this pencil more than this, right? So you can see that there are some instance specific properties. So we can see in real world, when you see everything as objects, they all belong to classes. For example, all of us are human beings. Human being is a class. I am an instance of a human being. I'm wearing a hat and specs and I look like this. You might be looking a little different, but you're still an instance of human being, aren't you? Assuming you're watching YouTube video and you're not a cat, right? So the point is, we have a class which represents the main behavioral traits of all objects belonging to that class. And there are different classes. We have a class for a pencil, we have a class for mouse, we have a class for a teacup or human beings, computers. You get the idea, right? Similarly, when Python deals with information or data in a program, at a very high level, it tries to classify all of those ingredients of a program, which can be represented with a label. If you can label something in Python, whatever you can label in Python is an object. And these objects belong to some class. So in this case, the act of me using these quotes to create something tells Python to create a string object. It's a string object that has these characters 1, 2, 3, 4, 5. That's what it means. And to know what's the type of an object, use the type construct. And now if at all I want to, if I say maybe, v is equal to 1, 2, 3, 4 this time, no quotes. Print type of v. What does it say? Type int. Int is short for integer. It's a kind of number. A number without decimal points, no floating points. But if at all I try this, so v is equal to 12.34. You can see I put a decimal point there. And now when you try running this, it shows class float. So we can use type to identify type of an object passed as its argument by the identifier. So you cannot really pass an object. You can only pass references to objects. The identifiers act like references. Think of type as one entity and you have the number somewhere in memory. You want to tell type, find out what's that type of that object in memory. How do you do that? You cannot take that object and pass it on to type. Rather, you have a reference to it. That's an identifier. You pass an identifier. Through the identifier, it sees that reference, sees that object and says, oh, that's an integer. Or that's a string. That's a list. So when you're passing arguments, you're passing always as references. Okay. So as v acts like a reference to this 112.34, or in this case 1234, or in this case 12345, and type identifies a type of the object based on what is passed as a reference to it. The identifier as a reference. Okay. I told you about all these aspects about types and how do you identify types. Now coming to expressions, as I told you literal value representations, right? Look at numbers a little more detailed here. I can represent number like this 1, 2, 3, and obviously this is an integer. I'm going to try b is equal to 3.14, and now you can see the type itself is different. It's a floating point value. A is an integer, b is a float. So a is representing an integer object, b is representing a floating point object. A floating point has all these decimal values. So you can do a little bit of floating point arithmetic on it. You can also represent numbers literally as another form. It's not very popular, but it's supported in Python. If you are a mathematician or a data scientist or anything to do with pure science, you'll appreciate this. You can say 4 plus 5, j. This looks like an expression, but it's not. This is a complex number. You can see that. Print type of C. So this is a literal notation of a complex number. To represent complex number, you say the real value plus imaginary value followed by a j. In some languages, they use a small I. I think it's based on the mathematical notation. In math, sometimes they use imaginary with the I, but in Python, they use j. I think it's got to do with the US standard versus the European standard. So it's all about that. I think in Europe, they use j, I guess. Even in India, we used to use j. So that's how it is represented, right? So this has two parts, real and imaginary, right? That's how it is. It's purely mathematical. If you are into statistics or advanced math, I guess you would have definitely encountered complex numbers and you know what it is, right? So I'll not go deep into that part in this session though. Coming back to integers themselves can be literally represented in different forms. For example, if I tell a is equal to 1, 2, 3, 4, this is a decimal literal notation of integer. Because when I print a, is always printed in decimal format. Print function, if you pass an argument that's an integer, it's going to take the integer's value and print it in decimal notation, always. That's a default, right? If at all I try maybe b is equal to 0x, this time I can use 0x out here and 0 small x or capital X, both will work. You can try maybe some numbers like say 1a f c. I just randomly chose some digits there. And this is how you represent hexadecimal. Literal notation of integer. Hexadecimal is base 16 and it's a very common format used in representing pointers and a lot of low-level stuff because it's very easy to convert hexadecimal to binary and binary to hexadecimal. Converting decimal involves a little bit of math, like 2-power maths, right? That you have to say, if you have 1101, for example, you have to say 1 into 2 to the power of 0 plus 1 into 2 to the power of 1. So you need to do all that math. But when it comes to hexadecimal, you can have a simple lookup. So if you know how to convert binary to hexadecimal for the first 16 digits, hexadecimal digits to binary, you just remember that. It's pretty straightforward. Because of straightforward conversion methods, I think this has become quite popular for representing low-level data or raw binary data. So, but when you print B, remember, you are representing a number as a programmer in hexadecimal literal notation, but internally stored in binary format in memory. In RAM, it's stored in binary format. If you ask Python to print it, it's going to print in decimal format. You can see it's. This 1AFC in hexadecimal is 6908. Let me try some interesting numbers. Like say, if I try 0xa, What do you think it is? It's 10. Because after 0 to 9, the next value is A in hexadecimal, which corresponds to 10 in decimal. You can see that. It's a proof. Or if you try something like FF, what do you think it is? It is 255. Magic numbers, right? 255. The last possible value in 1 byte. This F takes 4 bits, another F takes 4 bits, so totally it's like 8 bit. In 8 bit, the maximum value you can represent is 255, unsigned value. Okay, so that's what you can see here. So you can look at this. This is how you can represent hexadecimal literal notation of an integer. But when you print it, it comes up in decimal. Some of you might ask, no, I want to print back in hexadecimal. What do you do? There are functions, built-in functions to support that. There are 2 ways to do it. One of them, the easy ways for now, using built-in functions, you can just use hex of b. What hex really does is, given an argument that's an integer, it prints the integer in hexadecimal string format. The return value of hex is a string, which is representation in hexadecimal. In fact, I will show you something. I'll create another cell here. In this cell, I'm just going to try A is equal to 0x10. This is hexadecimal, by the way. Though I put 10 at the end, because there's a 0x prefix, is a hexadecimal 10, which I believe will be 16, if I'm not wrong. The value is 16 in decimal. If I want to verify that if it's a print A, you can see it prints 16. But now let's do this. I'm just going to try B is equal to A. If I try to print type of B, what do you think it is? Class integer. It's an integer. A is an integer. An integer is created. When I assign A to B, you're just having one more reference to the same data. So A and B are going to refer the same value, right? Which is integer by nature. So if you just say type of B or type of A, and if you try to print A or B, you will get the same value, same type. But I'm going to do something. I'm going to say C is equal to hex of A. I'm going to print the value of C. Then I want to print the type of C. I'm printing the value and the type. What you observe here, when you print the value, it prints as is 0x10. You can see that 0x10 is printed. But look at the type. It's a string. In fact, if you just put it in a REPL like this without using print, you can see it shows up in quotes. It is an indicator by the REPL telling that this value is treated as a string. So the hex function takes in an integer and returns a hexadecimal string representation of that integer. An X string representation of an integer. Okay, that's what hex does. If you want to print in binary, you want to print, so you remember, this is not just for hexadecimal values. You can print anything in hexadecimal. For example, I could say A is equal to 100. I want to know what the value of 100 is in hexadecimal. I could just print X of A. 100 in decimal is 0x64 in hex. And now, if you want to print in binary, if I say bin of A, binary is represented with 0b in the prefix. You can observe that. But its output is a string. It returns a binary string representation. Returns a binary string representation of an integer. I can say binary string representation of an integer's value, to be more specific, let's say, right? So it just returns that. Returns a binary string representation of an integer's value. This does the same in hexadecimal. When you use hex. And there's also another built-in function called oct. So when you say oct of A, you get the octal number. These are 3 popular formats: binary, hex, and oct format is used in various use cases in programming. So that's the reason why there are helper built-in functions to represent them. If you want to represent literal numbers in the same form, you can also try this. I could say A is equal to, this is 100, this is decimal, B is equal to 0x 100. This is how you represent hexadecimal. All these are literal notations, by the way, right? You can say C is equal to 0 small o 100, which is octal, and D is equal to 0b 100, which is binary. All of these are different literal representations of integer. So if you try to print all of these values, by default, it'll print the output in decimal notation. So when you try to print A, B, C, D here, 100 is 100. Decimal literal notation. Output also comes up in decimal format. But here I represent it literally in hexadecimal. But when you try to print it by default, it's going to print in decimal notation, which is 256. If I try 00100, you can see that the decimal notation is 64 and 100 binary is a value 4, right? You can see 00, 01, 10, 11, 100. If you look at the binary numbers, right? 4 is 100. So these are the ways you can represent literal data in different formats. 0x, 0o, 0b prefixes. And yes, you should also note something in Python. If I try this, if I try to say maybe 0, 0o, if I try maybe 896, you can see my VS Code is already highlighting this in red. So it's an error. Just try running this. It says invalid digit 8 in octal literal. If all you use 0o prefix, the digits can only be between 0 to 7. If you put a 0b prefix, the digit can be only 0 or 1. That rules are checked while parsing the syntax. It's a syntax error. And I talked about syntax error in the last session, if you remember. These are parse time errors. So you put this kind of code in somewhere in the 100th line, not a single line of code will execute, right? I guess you got that. So there's something you should know about the notations, literal notations. So integers can be literally represented in all these formats. Now, when you're dealing with integers, you can perform various operations on them. What are the operations you can perform? Well, you can add, which you all know. I can say 1 plus 2, the addition. I can subtract by using 10 minus 5, subtraction. We can multiply. For multiplication, you say 10 into 5. It's multiplication. So addition, subtraction, multiplication. I'm not labeling this because these are obvious things you people should be aware of when you learned arithmetic in school. It's all the same, right? So all these are arithmetic operators. And these are also called as binary arithmetic operators because they take 2 operands. You have an operator that takes 2 operands, but you can chain load them. You can chain load. What is chain loading? You can say 1 plus 2 plus 4 plus 5 into 6 minus 3. So basically this, the addition happens based on order of precedence. First, the multiply is going to happen first, followed by addition, followed by subtraction, right? If you look at this, right? Maybe you can verify that with your arithmetic logic here. It's going to work. So you can, all these binary operators can be chain loaded across this way. Now, what are the different arithmetic operators you have here? Well, I'll just put a note here, okay? You have addition, subtraction, multiplication, division, but that's not all. You have floor division, and you have power of operator. These are the standard arithmetic operators supported by Python. And yes, I forgot to mention modulus operator. After division, I'm going to add another operator, that's modulus operator. I'll tell you all these operators, pretty straightforward. Addition, subtraction, multiplication is fairly obvious. Division is an interesting one. This requires a little bit of unlearning if you come from an existing programming background like C or C++ or even Java. What is 5 by 2? Ask a C programmer. He's going to report and say 5 by 2 is 2. 1. No, it's not fully divisible, right? 5 by 2. What about the remainder? So if you come from C background, an integer divided by integer is an integer, which is just a quotient. That was the case all the way till Python 3.0. Since Python 3.0, they remedied this. They said, oh, that's not the right thing. Mathematicians wouldn't agree. Division always returns a floating point. Always. This is why it's called as true division now. See, it's 2.5. It's not 2. It's 2.5. The 2.5 is of type float. If you go and do a type check of that result, it'll be a floating point value. Even if you have a number that's properly divisible, like you try 10 divided by 2. 10 divided by 2 is 5, right? But you won't get 5. You get 5.0. This can be sometimes an annoyance in certain expressions. Python is strongly typed. There are certain expressions like some functions that expect an integer. You pass a float, it's going to flag off an error. I might be jumping too forward, but I'll show you an interesting trick here. I mean, I'll be covering more details in the future session, but I'll tell you where this can break apart. Is when you use some idioms like, say, for I in range of, x divided by 2. And, if I print I, for example. Don't worry about this. It's just a Python statements. You can say I'm using compound statement and all these. I'm jumping a little forward. Don't worry. Just, I'm going to make you focus on this part alone. Okay. I'm going to try x is equal to 10. Try running this. And you can see an error. Type error. Float object cannot be interpreted as integer. Where? In this line. In this line, there is a float object somewhere. Which one would it be? X divided by 2. Range construct. Range construct. I call it a construct. It looks like a function. Again, this is a type. Can be called like a function. That's what range is. Okay. So you'll see that there are many types which look like functions, look and feel like functions in Python. You don't have to worry about it. You can just call it like a function and say it's a function. Nothing wrong in it. But internally, they are types. Okay. So the range construct, when you pass an argument, the arguments must be integer. If you pass a floating point, it's going to flag off an error. If you simply said like this, if you just, range of x like this would have printed some values like 0 to 9. Yeah, this is a loop. It's a for loop, which I talked about. Jump too forward. Don't worry. My focus is not teaching you for loop. We have a dedicated session for that. Maybe 3 sessions just on for loop. 3 hours on for loop. Okay. Prepare for that. But now I can tell you this range takes an argument which must be integer. But sometimes if you have an expression where I say I don't want to compute 10 times, but 10 by 2 times, right? Maybe I want to say x by 2 times here. What are the value of x's? Divide by 2. I want to count that many number of times. Throws an error. What is a fix? Here's where the fix is. If you want the result of division to be an integer, use // This is called as floor of division, also called as floor div operator. So when you run this is the outcome. Getting my point? So here, if you remember the list of operators I showed you a divide operator. The divide operator always returns a floating point. So you get true division. So if at all I say 5 by 2, you'll not get 2, you'll get 2.5. But if you want the result as only the quotient as an integer, then use /. This is called floor div operator. So I'm just going to make a note here. // is called as floor div, also called as floor of division. The floor value after dividing numbers, that's the quotient, and result is an integer. Returns integer based on division. This is assuming the operands are integers. Some of you might ask, what if the operand is a float? What if the argument I pass to is float? These are the kind of questions you should have, and you should try it out. That's the beauty. So you got this question. Most people ask me this question. When they sit in the front of a REPL, you should try it out, isn't it? So when you try 10 point, I'll say 5 point, let's say, okay, okay, 10.0 double forward slash 2. See, 10 double forward slash 2, 10.0 double forward slash 2. What if it is 5.0 double forward slash 2? Do you see something? Look at 5, look at this 5 by 2, 2.5. 5.0 by 2, 2.5. True division. 5 double forward slash 2, there's 5, floor div by 2, it's 2. But if any one of the operand, either this or the other, is a float, the result is a float, but it is still the floor value, not the true value, the floor value of division. That still applies. For floor div, if both operands are integers, the result is integer. If any one operand is float, the result is float, but it's not true division, it's floor division still. There's something that you just observed. These are some subtleties that you should explore and try out. When you're learning any language, you should try out all the possibilities and find out what happens if I do this, what happens if I do this, what happens if I do this. And that's how you gain better expertise, right? From the basics. All right. Have I run out of time? Okay, we still have another 5 minutes. All right. So I talked about all these arithmetic operators. The last one I forgot to mention is this. Yeah, I think I talked about addition, subtraction, multiplication, division. Modulus is remainder of division. So this is not unique to Python. It's been there in most of the mainstream languages. I know I started knowing it from C programming language. So when I say 5 percentage 2, it returns the remainder of division. After dividing 5 by 2, what is the remainder that you get? The quotient you get by double forward slash. The remainder you get by percentage. Also called as modulus operator, right? It is also called as a modulus operator. Nothing but remainder of division. Used in interesting logic and algorithms sometimes, right? We'll work on that. The next thing I should talk about, which is unique to Python, not unique, I mean the syntax is unique to Python, but this feature is there in certain other languages like Fortran, MATLAB and all that, right? That is the power of operator. So if at all I say 5 double asterisk 2, just like link 5 to the power of 2, which is nothing but 5 into 5, right? If at all I want to do something else, let's say 2 to the power of 5, I can type 2 raised to 5. The double asterisk is a power of operator. In some languages, people who come from Basica, Fortran, right, use a cap symbol. The cap symbol has a different meaning in Python, coming from C background, right? It has taken some features from C. It's a bitwise operator. It's called XOR operator. So they cannot use a cap symbol for power of. They use double asterisk here, right? So when you use this, you get 2 to the power of 5. 2 into 2 into 2 into 2 into 2. 5 times. Let's try 2. And here's an interesting one. How do you find the square root of a number? Square root of a number. If you come from other programming language backgrounds, especially C programmers will look for a function, sqrt function. Include math.h, sqrtl, Java developers. Import java.lang.math. I think that's already imported, but you'll say math.sqrt of 2. Python way, don't import math and all that. Just do 2 to the power of 0.5. The law of indices that we would have learned in elementary algebra. A number raised to its half is the square root. You don't need a function now. It's a built-in feature. If you want to find the cube root of a number, no problem. But only thing is that you have to be a little careful about the round off issues. So you could actually say 2 to the power of 1 by 3 is a cube root. It's not going to be accurate. It's an irrational number, so it's going to give you accuracy to some extent based on the CPU's capability, the floating point unit's capability. Mostly it'll be 64-bit, right? So that's the accuracy that you'll get. We'll leave it that, right? So these are the arithmetic operators that you should be aware of: addition, subtraction, multiplication, division, modulus operator, floor div, power of operator. I think we ran off to 1 hour. I'll continue the next session where I'll talk about comparison operators, bitwise operators, and other features, right? Expressions related to them. So I hope you found this particular session useful. So if you have learned something, do let me know. If you have any questions or doubts, as usual, you can ask me on comments. And yeah, do like, share, subscribe, right? So it reaches more audiences, and that's how YouTube works, right? Thank you very much. So hope to meet you in the next session.